Now that we've had a brief introduction to machines, we are going to learn about the simple machines. There are 6 different simple machines that we are going to learn about. This video is going to cover the lever. So first we'll start with, what is a lever? It is a bar that is free to pivot about a fixed point, and that fixed point is known as a fulcrum. There's a famous quote by Archimedes that said, "Give me a place to stand and I will move the earth," because levers make lifting heavy objects much easier because of the mechanical advantage that they provide. The area of the lever where you apply the force, the human, that is known as the effort arm. The other side of the lever that is going to be doing the work for you is the resistance arm, because the machine is doing that work for you. And then the fixed point that it pivots on is known as the fulcrum. So here's your equation for ideal mechanical advantage of a lever. Now this should look really familiar to you. It's the exact same equation that we just got done using. It is the same thing. Okay, the difference here is that we're going to have an L in place. This is for length, but length is a form of distance, so we're still going to measure length in meters. Okay, so you have the effort arm length in meters, so the length of the arm that the human is inputting their work on. And then you have the resistance arm length, so this is the length of the arm measured in meters of the machine's work effort. Okay. Now, in order for this to work, the effort arm length must be greater than the resistance arm length in order to multiply the force. Okay, so the effort arm must be longer than the resistance arm if you're going to increase the force. Here's your triangle so that we can continue to use that same method. So there are different classes of levers depending on how they work. The first class lever is one that can either increase force or distance, or it might do neither. It might just change the direction of the force. But in any case, it always changes the direction of the force. An example of a first class lever is a seesaw. That is a classic one. Also, scissors are an example. So you can see here the fulcrum is located in the middle, and then the effort and resistance arms go to either side. Okay, so think of this as a pair of scissors. The fulcrum would be the screw that holds the two sides of the scissor together. The effort would be the handles, and the resistance would be the blades. Okay, or you can think of this as a seesaw with 2 kids playing on it, in which case the effort arm and resistance arm switches back and forth as they move up and down. Okay. I do highly suggest drawing this diagram in your notebook and possibly researching some first class levers so you have several examples, because on your test I will ask you to identify several examples and tell me what class they are. Okay, so this is a first class. Then we have a second class lever. This one always increases force. Always increases force. And you'll see that the fulcrum is far away from the effort and that the resistance is in the middle. Okay, an example of this is a wheelbarrow. So the wheel of a wheelbarrow would be the fulcrum. That's the pivot point that as you lift and lower. The effort would be the handles where you do the lifting, and then the resistance is the actual barrel part where you put whatever it is you're trying to move. And so it makes moving, you can move much heavier objects using a wheelbarrow than you could just carrying it. Another example is a bottle opener or a staple. a stapler. And finally, we have third class levers. These ones always increase distance. They always increase distance. Okay, notice here we have the fulcrum near the end again, but now the resistance is far away from the fulcrum and the effort is in the middle. Okay, so notice how that is different. Look back at the diagram you just drew for your second class lever and see how that is different with this third class. Okay, an example here is a broom or a baseball bat. So you can think of a baseball bat here. The effort, this is where the baseball player is holding the bat, and the end of the bat is where it pivots as the baseball player rotates their wrist, and then the ball hits the end of the bat. Okay, and then the ball flies a very large distance if they make good contact. Okay, so baseball bat is a good example of a third class lever. All right, now let's do an example problem and see how to calculate your mechanical advantage of levers. You use a plank to lift a large rock. If the rock is 20 centimeters from the fulcrum and the length of your effort arm is 140, what is the plank's IMA? Okay, so let's draw a diagram so we can picture how this is working. Okay, so we are using a plank to lift a large rock. Okay, the entire length is 160 centimeters because the effort arm is 140 and the rock is 20 centimeters from the fulcrum. So this distance is 20. Okay, so let's analyze and see what we have so we know how to put it into our equation. So we have the resistance length is 20, so that's what the machine is doing. We have our effort length is 140, that's where the human is putting in. And we need to know what is our mechanical advantage. So if we have our triangle here, we cover up the IMA, we see what do we need to do? We need to do L sub E divided by L sub R. So we need to do human effort divided by machine resistance. Okay. So that means we need to do 140 divided by 20, and we get 7. So my mechanical advantage is 7. And remember, mechanical advantage never has a unit. Now, in this case, I did not have to do any converting since both of these were the same unit, and there should be a unit there. That's my typo. That should say centimeters. If they are the same unit, then you can just plug it in to the equation. Just be wary if I give you a problem with two different measurements, one is centimeters and one is meters, you have to convert one of them to make them match. Okay, so your two lengths must be in the same unit, whether that's centimeters or meters or kilometers. If they're already the same, you can just plug them right in. If they're not the same, you have to convert. So do be careful about that. Okay, all right. If you do not know how I figured out this problem and got this answer, please get into contact with me so that I can help you out, because up next is your independent practice on calculating mechanical advantage of levers.